vector space. So let us say we have a finite dimensional vector space over a field, let us say F, and W a subspace of B. Then what we know is each of so W, and this is V hat and W hat, all of them. Annihilator of W here is also finite dimensional. We have proved that if dimension of say P over F is n, and the dimension of W over F is say m, then what we know is about the annihilator. Annihilator of W in F, if you recall, is the set. So this is the set of all this is subspace of V hat. So this consists of all F here in V hat, such that Fw is 0 for every W in W, and this is a subspace of V hat, and this is also finite dimensional, and the dimension is R, where R is n minus n, dimension of V minus dimension of W. So this is what we have proved. Now we want to see the application of the annihilators. So as an application of annihilators, let us take an application of this result. So an application of this result, what we see is in the form of the following theorem. So let us say the theorem. So suppose we have a system of homogeneous linear equations. So if we have a system of homogeneous linear equations over F, namely, let me write the system of equations. So say A11 x1 plus A12 x2, and this is say A1n x, and this is 0. Second equation, let us say A21 x1, A22 x2 plus A2n x, and this is 0. And let us say like this, there are m equations. So am1 x1 plus am2 x2 plus, and say amn xn is 0, where the coefficients aij, they come from the field F. So there are m equations in n unknowns, and such that this ai1 x1 plus ai2 x2 plus ain xn is 0 for every I 1 to m. So these are the m equations, and it's a linear system. If no product of xi's are involved, and the homogeneous, as the right hand side is 0. So we want to know is meant by saying that a solution. So a solution means we look for the, say, vectors which satisfy x1, x2, xn, which satisfy these equations. So AIs are known. The solution means the vector, say, V. The solution of the system means solution of the system means a vector, let us say here V, so that x1, x2, and xn. Here, now naturally, these are, let us take this here. If we are interested in solving over f, so that this is in V, and where V is Fn for f, such that these each of these equations is satisfied. That means Aij, and this you can say this ith equation. If I have to write, then this I is fixed and j is equal to 1 to n, and this is xj is equal to 0 for every I 1 to n, let us say n. So we look for the vectors, say v, x1, x2, xn in Fn over f, such that each of these equations is satisfied, means summation j over 1 to n aij xj equal to 0. This is ith equation. So for every equation, therefore, I is equal to 1 to n. And we said that this is a solution. So we want to know about the solutions. And we also are interested in knowing linearly independent solution. Because a nonlinear combination of solutions is also a solution, obviously, you can see here. So if V satisfies this equation, W also satisfies this equation, and V plus W will also satisfy each of these equations. And a scalar multiple of alpha V also will satisfy. So what we see here is that a linear combination of solutions is also a solution. So since a linear combination of solutions of the system is also a solution. You can call, if you want, this say star is also a solution. We are interested in finding linearly independent solutions. All right, so let us take that U. Now, let us take U to be the subspace of V spanned by the vectors you can call, say, the vectors so the Cellini.
No, sir.
इसका पेन डिस्चार्ज हो गया पूरी तरह से.
Yes,
Anyway,
sir.
let me recall what U is. So U is the subspace here of V. V is Fn over F, which is spanned by the vectors, let us say, A11, A12, A1n, and second vector say A21, A22, A2n, and say mth vector am1, am2, amn. Let me see if it is charged a little. This is so a11, and here let us say this is a1 n, and like that a21, a2n, and like that. So this is am1, amn. So these are the spanned by of V. V is what? Fn over F. So suppose this is the subspace spanned by these m vectors. Now, these all may not be linearly. So what we now want to see is here. Let us take the dimension, and also let us take the dimension of this U over F. Let us say R. Now, since this is a subspace of n, so it cannot exceed n, and so is finite. So V is finite dimensional, and we have a subspace now here, which is also finite dimensional, and let us say its dimension is R. So, and this R is called the rank of the system that we already had. This R is called the rank of the system of equations that we have stated in the beginning. And you will soon see that why it is called rank, in the sense that you have solving the system of linear equations. All right. So what we see here is that let us take now we want to compute actually the annihilator. So let us say any f in v hat. V hat is the hat of Fn over F hat of this. So what this will mean that this is say x1 v1 plus x2 v2 this let us take if b is standard basis, let us take v1 to be, let us say 1 0 0 0, and like that say vn to be 0 0 and say 0 1. This is the standard basis. For Fn over F. And correspondingly, B hat, which is V1 hat, V2 hat, and let us say Vn hat is the standard ordered basis for V hat over F. So any F and V hat therefore is a linear combination of these vectors V1 hat, V2 hat, Vn hat. Then this F can be stated as a linear combination of x1 v1 hat, x2 v2 hat, and so on, x and vn hat, where these xi's are coming from F, as this is a vector space over the field F. Okay, so what we have started with, let us say U be the subspace of V, which is spanned by the vectors, the n-tuples m in number. Any arbitrary tuple is of the form ai1, ai2, ain, or I1 to m. So these are the m vectors, and suppose out of them r are linearly independent, or say the dimension of this u or f be say r. This r will not exceed n naturally. Now think of the dual. Think of the dual of v. So v hat. V is fn over f, and take the standard basis for v over f, say v1, v2, vn. So each vi will be of the form everywhere 0, and at the ith position for I1 to n will be 1. With this order specified, we also can associate a basis, say b hat for v hat over f, and these basis elements which are homomorphisms of v into f, denoted by say v1 hat, v2 hat, vn hat. Then this f naturally, any element of v hat is a linear combination over f, say x1 v1 hat, x2 v2 hat, plus and so on, say xn vn hat. So what we see here is if you have any element here, say in the annihilator, so any arbitrary element will be a linear combination of this type. Now we want to see what about the annihilator of U. So what we claim is that any G in the annihilator, if you have, and if G is of the form, you fix up the linear combination in V hat over F, then correspondingly you will have a solution of the system. So what we claim as such is this following, that if G, and let us say G is x1 v1 hat, x2 v2 hat, and so on, say xn vn hat, this be an element. This is in v hat naturally. So if this is an element here in the annihilator of U, so this is a subspace, so naturally we know is of V hat. V hat here is Fn over F hat of this. Then what will happen now? Since this V1 hat, V2 hat, Vn hat are the basis vectors here of V hat. So writing G as this linear combination is unique. That means for a given G here in this annihilator, xi's are uniquely determined. Once they are uniquely determined, you can think of this vector, that this x1, x2, and say xn. This vector is in V because each xi is from F. So this is from Fn over F. Now what we claim is that if G is in the annihilator, this vector in Fn over F is a solution of this system of equation that we have stated in the very beginning, and vice versa. Converse also is true. That means if there is a vector, say x1, x2, xn in V, and you construct then a homomorphism of V into F, namely G, x1 v1 hat plus x2 v2 hat and so on plus xn vn hat, then this is going to be in the annihilator of U, where U is the subspace of V spanned by the vectors a11, a12 and a1, and m tuples in number, mth tuple will be am1, am2, amn. So both ways. Now you can quickly see this, for example. So for the proof, let us take that this G belongs to the annihilator of U over F. So what does it mean? Now G is this x1 v1 hat, x2 plus x2 v2 hat and xn vn hat. So now this G where G is x1 v1 hat, x2 v2 hat and so on, x and vn hat. Now, if this is so in the annihilator, that means so it annihilates every element of U. That means this is 0. Now, what is 0? That G of when you apply on each, so this is on each element from U. So this in particular, so this is G, it will annihilate every basis vector also. So G of U will be 0 for every U in U. So in particular, for every basis vector also. So this is 0, that this is G. So AI1, AI2 and this is AIN for every I1, 2 up to say M. So for example, when I is 1, what we get here? That this is 0 is equal to G of A11, A12 and so on, A1N. Now this is a 0 means what? Now since these AIs are from F and this element is in V, that means Fn over F, since A11, A12, A1N, this is in V, V is Fn over F. And B here V1, V2, Vn, where we know is the standard basis. Or V over F. And V1 we know is 1, 0, 0, 0, V2 is 0, 1, 0, 0, Vn is all zeros, last entry 1. So what we can write therefore, now this as a linear combination of the basis vectors. So this vector here in U is a vector in V for which B, V1, V2, Vn is standard basis. And therefore this vector is a linear combination of the basis vectors V1, V2, Vn. Now this linear combination also we know. What is the linear combination? So this is A11 V1 because that only will contribute as the first coordinate as a1, 1, because all other entries are 0. So this linear combination is, so what we have is that a11, a12, a1n is actually equal to a11 v1, a12 v2 plus a1n vn. So 0, we have g of this a11, a12, a1n will amount that this is the g of this is 0, a11 v1, a12 v2 plus a1n vn. All right. So this is 0. Now g is a homomorphism of v into f, and g is already we know that this is x1 v1 hat, x2 v2 hat. So since g, we know that x1 v1 hat plus x2 v2 hat and so on, x and vn hat. So what we get here as a result that this is 0. So this is x1 v1 hat, x2 v2 hat, x and vn hat. This operating on a11 v1, a12 v2, and this is a1n vn. Good, nice. So this is what it is. So now because of this you can write therefore either way. So since this is also linear combination of homomorphism, so this is also a homomorphism. So this will apply on each of them. So you get that this is same as depends on how do you want to write. So this is same as, for example, this x1 v1 hat, x2 v2 hat. This is a homomorphism, therefore x and vn hat. This applies on a11 v1. So this is a11 v1 plus and so on, and like that. The same is applied here on x and vn hat, like that, on a1 and vn. Because this is a homomorphism, so it preserves the sum. Now this scalar can be pulled out. So this is a11, x1 v1 hat, x2 v2 hat, and this is x and vn hat on v1, and like that. So a1 n x1 v1 hat plus x2 v2 hat, x and vn hat on v. Now because this is the linear combination of homomorphisms, so you can use the fact that if T1, T2 are two homomorphisms, T1 plus T2 on V is defined as T1V plus T2V. Now with that, therefore, this will be A11 and this will be X1 V1 hat. So this is X1 V1 hat on V1 plus X2 V2 hat on V1, and like that, x and vn hat on v1. And the last one, therefore, like that when you write. So this is each applied on v1, and here like that. So last will be each applied on vn. So this will be here. So a1n, and this is x1, and this is your v1 hat applied on vn, and like that. The last one will be a1n xn vn hat applied on vn. So this is I have taken inside also even anyway. So what you can see here is that because of the property that Vi hat Vj is Vi hat Vj, this is delta Ij. That means this is 1 when I and j are equal and 0 when I and j are distinct. So the first bracket will consist of only one term, that is namely the first one. So this will be a11 x1 and all others will be 0. The second will have like that a12 x2 and rest all will be 0. And the last one, this will have a1 n, and this last term only will contribute. So this will be a1n xn. That's all. And left hand side is 0. So what we get is that 0 is equal to a11 x1 and a12 x2 and so on a1n xn is equal to 0, which is the first equation of the system. So likewise, you can see all other equations are satisfied. So likewise, we can see that all other equations are also satisfied. All other equations are also satisfied. Okay. So we started with the G in AU. So thus, if G of the form x1 v1 hat plus x and vn hat is in the annihilator of U, then what we have here is that we have a solution. Correspondingly, x1, x2, xn in Fn over F is V is a solution of the system. All right. Conversely means so. Conversely, if we have a solution, so let us take x1, x2, xn in Fn over F, that is V, is the solution of the system. Is a solution of the system. That means each equation is satisfied. So Aij, Xj, and J1 to n, 0 for every I, 1 to m. This is the meaning of the solution of this system. So conversely, suppose these n tuples are of the form in V such that each equation is satisfied, then what happens to the corresponding G? Then let us take G to be x1 v1 hat plus x2 v2 hat and say xn vn hat. Now this belongs to the annihilator of U. Yeah, this is subspace of V hat naturally. For this you can see that this G of every basis vector we prove is 0 and therefore G of every U in U 0. So for say Vk here in the basis B, GVK. What is GVK? GVK is G is our x1 v1 hat plus x2 v2 hat xn vn hat applied on Vk. This is G. Now what we know is that Vi hat Vk is delta Ij. So from here we shall have only one term that will come from xk Vk hat, because all others will be 0. This will be xk Vk hat on Vk, since once again. So this is Vi hat Vk is delta Ik. So this is 1 when I and k are equal, and 0 when I and k are distinct. Vk hat over Vk is 1, and therefore this is simply xk. So this happens. So what we have got is that this GVK is simply xk. Nice. So each Vk is annihilated. So this is for all k 1 to n, and since Vk's are the basis vectors, since these are the basis vectors here, what we get is that this G, this is uh, that this G belongs to the annihilator. So it annihilates every vector which is linear combination. So this annihilates every vector. So G belongs to the annihilator. So if it annihilates every basis vector, it also annihilates every vector. So what we have got is that G will be in the annihilator. So there is a one-to-one correspondence. Hence there is a one-to-one correspondence between the solution. What is the one-to-one correspondence? The solution between the solution x1, x2, and say xn in fn over f, and the linear functional what is this linear functional? G. G is x1 v1 hat plus this xn vn hat. And where is it? This is in the annihilator of U. So once there is a one-to-one correspondence between the solution and the corresponding linear functional in the annihilator, naturally the number of linearly independent solutions therefore would be the dimension. So the number of linearly independent solutions will be the dimension. So this will be n minus r. So this gives that the number of linearly independent solutions is the dimension of the annihilator. Is the dimension of the annihilator of U over F. And remember, this is the dimension of V minus dimension of V over F minus dimension of U over F. Now V is Fn over F, so this is N, and dimension of U we have assumed this as R. So the number of linearly independent solutions is N minus R. Call it, say, whatever is this number. So this naturally will not exceed. This is definitely will not exceed N, and in fact will be less. So the number of linearly independent solutions here is N minus R. You can also deduce from here that if the number of nodes, that is N, is greater than M, in that case, there is always a solution. You can also conclude that in particular, if N is greater than M, M is the number of equations. In that case, there is a solution. There is always a solution. And this is a non-trivial solution. Because in that case, you will have that this N minus R is positive. So you always have a non-trivial solution. That is a solution say x1, x2, and say xn in Fn over F, where not all of x1, x2, and xn are zero. So it always will have at least one non-trivial solution. We shall have some examples now. So before we take up the example, we just have a look on what we have done. And now let us have just a few examples. Just a moment. The pen is charged, so one or two examples quickly we can have. So let us take this exercises. So suppose V is a finite dimensional vector space. W1, W2 are subspaces. Let us take say V over F be finite dimensional vector space over F. W1, W2 are two subspaces of V. Then what we know is the annihilators of W1, annihilators of say W2, and you can also have this annihilator of W1, W intersection. Each is finite dimensional, and you can also see that is each of them is a subspace here of V hat, and finite dimensional is finite dimensional over F, and moreover what you can check is that the annihilator of the intersection is actually the sum of the annihilators plus annihilator W. So for this what you can see is the following. So for a finite dimensional vector space and its subspace, we can prove that annihilator of these W1 plus W2. You can all check that first of all that this is for any two subspaces W1 plus W2. This is actually the annihilator W1 intersection annihilator W2. First, this you can see that this can be seen easily. So you just can take here that these sides are equal, and then you can obtain what we wanted about the annihilator W1. So this I leave for you, and using this what we can prove is so you can apply this now. Now let us take that V had to be say U. This is true for every vector spaces. So let us make that this is U1, 2, so that we can apply this. U1, U2, U1, and U2. For every U1, U2 subspaces here of V. This is for you. So this for you, and using this we can prove this. Now, for put this say let us say U. Is the result that you can prove. So this is for you. Now, put this U as V hat. So this is the dual of V over F, and dimension of we know that the dimension of U, this is the dimension of V hat over F, same as the dimension of V over F. So this also is finite dimension. Annihilator here, annihilator here, W1 intersection W2, this is the space of U, that which is V hat, is also finite dimension. Is also finite dimensional because V hat is finite dimensional. Now U1 plus say U2, if you put U as the annihilator of V hat, call this U1 as the annihilator of W1. If U1 is the annihilator of W1, U2 as the annihilator of W2, then this result. Then this result will give you this, that. So annihilator of U1 plus U2, that means here annihilator of annihilator U1 plus annihilator U2 is the intersection of the annihilator of U1, that means annihilator of W1. So this gives therefore as, so annihilator of W1, this is U1, plus annihilator of W2, this is the U2. This is same as the intersection of annihilator U1 with annihilator U2. So this is annihilator of annihilator W1 with annihilator of U2. Annihilator of U2 is annihilator of W2. This. Now we know that annihilator of annihilator gives me the same. So this is W1 intersection W2. So this gives me that the annihilator of this is W1 intersection W2. And once again equating the annihilators on both sides, if you take once again taking the annihilator, and this will make that if you take both sides annihilator once again. So what we get is annihilator of this is same as, so annihilator W1 plus annihilator W2 is the annihilator of W1 intersection W2. This is taking once again taking annihilators on both sides. Okay. So what we have got is that annihilator W1 plus annihilator of W2 is same as annihilator of W1 intersection W2. Just one more example we take up, and rest will be for you to do. Okay. So suppose we have F is the field of real numbers, and another example is let us take F to be the field of real numbers, and V is say F3 over F. F3 over F, that means is R3 over R. And we compute and let us take W is spanned by two vectors, namely say spanned by say 1, 2, 3, and another is 0, 4, minus 1. It is a subspace here of V. So we have perfect setup of finite dimensional vector spaces. Therefore, dimension is also. And we want to find out, now compute this annihilator of W. Now this is a subspace of V hat naturally. And let us take now B's standard basis, say V1, V2, V3, be the standard ordered basis for V over F. That means we know what is V1. V1 is 1, 0. What is V2? 0, 1, 0. And what is V3? This is 0, 0. Correspondingly, suppose we have suppose V1 hat, V2 hat, V3 hat. This is B hat, be the corresponding ordered basis for V hat over F. So we know that Vi hat on Vj is delta Ij. That means what? This is 1 when I is equal to j, and this is 0 when I is different from j. For each ij, 1, 2, 3. And this is for each ij. This is what it is. So what we want to know the annihilator. Now there are two vectors which span this. All right, so let us take these. This is say u1 and this is say u2. So let us take this is the vector u1 and this is the vector say u2. So w is spanned by u1, which is 1, 2, 3, and u2, which is 0, 4, minus 1. So what you can see therefore is that the annihilator of B is same as the annihilator of the basis. Because if it annihilates every vector, it annihilates the basis vector. Converse also holds true that if it annihilates every basis vector, it annihilates the subspace as well. And okay, so what we know is so the subspace W is basically is the linear span of these basis vectors, because this is spanned by this. So is this U1, U2, where what is U1? U1 is 1, 2, 3. What is U2? 0 and 4 and minus 1. Okay. So if F is in the annihilator, we want to know what is the annihilator of this. So annihilator of W is the annihilator of this linear span. That means this is the annihilator of span by annihilator U1, annihilator U2. Now if you have, let us take here, say F in the annihilator of W, then F must be linear combination of the basis vectors. Basis vectors are v1 hat, v2 hat, and v3. Alphas are from R. Alpha is from F. F is R. So what we want to know? So we want to determine these scalars alpha 1, alpha 2, alpha 3 such that FU1 is 0, FU2 is 0, and FU3 is 0. So this is in the annihilator. And F of every element in W is annihilated. And therefore, in particular, FU1 is 0, FU2 is also 0. Now, U1 is 1, 2, 3. So, FU1, therefore, now U1 is 1, 2, 3. So, with respect to the standard basis, this is V1 plus 2V2 plus 3V3. And with respect to this, this is 4V2 minus. So, FU1 is 0. FU1 is 0 means, so what you have here is, so 0 is FU1. F is what? Alpha 1 V1 hat, alpha 2 V2 hat, plus alpha 3 V3 hat, and this is on U1 is 0. U1 is what? V1 plus 2 V2 plus 3 V. And FU2 is 0 means what? Again, alpha 1 V1 hat, alpha 2 V2 hat, plus alpha 3 V3 hat. 4V2 minus V3 is also 0. What does this give me? So FU1, you can see that if you open the linear combinations, then only one term will come corresponding to V1 here. So this will be alpha 1, V1 hat V1, and when V1 hat is applied on all others, this will give you 0. So this will give me that the first equation, that this is alpha 1, V1 hat V1, that is alpha 1. Now alpha 2 V2 hat applied here, so this will give corresponding to 2 V2. So this will be 2 alpha 2 and this will be 3 alpha 3. The second one will give me FU2 0 means this will give me 4 alpha 2 minus alpha 3, this is 0. So when we write equations, it doesn't look nice that you write on the left, so you should write on the right. Okay. So this is equal to 0, this is also equal to 0. So you have got this system of equations. And you can see that there is a solution here. So that I leave for you to find out a solution here. So you can see from these equations that you can write this alpha 3 in terms of alpha 2 and substitute in this equation. So this will give you that a solution is of the form. So a solution of the form is, so this system as a solution of the form. So this is your minus 14 alpha 2 and 4 alpha 2. So form alpha 2 minus 14 and 1 and now this is in the, this is F3 F. Now for every alpha, so has the solutions of the form for every alpha 2 in F. So annihilator therefore is here alpha 2. So the annihilator. We have determined that so and F is of the form alpha 2 and this is minus 14 v1 hat. v1 hat. As you know. Okay. So f alpha 2 minus 14 v1 hat plus v2 hat plus 4 v3 hat, and alpha 2 is in hat. And the dimension, so the dimension of annihilator here of W for F is dimension of V minus dimension of W. Dimension of V is 3, dimension of W is 2, so this is annihilator's dimension is 1. So what we get is this minus 14 V1 hat plus V hat plus 4 V3 hat spans annihilator of W. And there's what we have got is that annihilator of annihilator. Okay, so the annihilator of W is of the form minus 14 V1 hat plus V hat plus hat. Alpha comes from F. F is here R. So this is the annihilator. So basis, we have got one basis vector minus 14 v1 hat plus v2 hat plus 4 v3 hat. So we shall stop it here, and other exercises, problems, we shall be uploading for your practice. So from my side, the dual spaces as such is. So thank you very much for your kind attention.